Good day. In this video, we will be talking about patterns and numbers in nature and the world. Many of us associate mathematics with numbers, operators, problem solving, quantifying, calculus, algebra, and etc. But in reality, math is as beautiful as art. But instead of paints, mathematicians uses numbers, patterns, and equations to express the beauty of nature. We can understand the universe if we see the pattern in the nature. Even the most famous astronomer said that mathematics is the language with which God has written the universe. If you want to understand the world using math, then there are 3 steps to follow. The first one is you need to find patterns. After which, you need to represent these patterns using symbols, notation, shapes, or numbers. And finally, you need to interpret these patterns. Pattern is defined as the regular, repeated, and recurring forms of design. So for example, the pattern in the zebra, the butterfly, and many more. In fact, there are many patterns around us. Like in some foreign countries, the sequence of the 4 seasons is always winter, spring, summer, and fall. In mathematics, it is a set of numbers arranged in a sequence such that they are related to each other in a specific rule. So for example, now this type of questions, like the sequence of numbers, the pattern, which is for spatial awareness, to test the spatial awareness of the students. Moving on, symmetry indicates that you can draw an imaginary line across an object and the resulting parts mirror images of each other. There are 2 parts of this, or 2 types of this, which is the bilateral symmetry, in which when you draw a vertical line in between the object, then the left side mirrors the right side and vice versa. The other one is the rotational symmetry, in which when you rotate the object, it will retain the same face as it did before you rotate the object. So just like the starfish, right? Moving on, the angle of rotation is just the measure of the angle that a figure can be rotated while still preserving the original position. The formula of the angle of rotation is equal to 360 degrees all over n. And the order of rotation is the more common way of describing rotational symmetry. So it is n-fold rotational symmetry. For example, the starfish, it is known as a 5-fold symmetry, and the measure of the angle of rotation is 72 degrees, since 360 degrees all over 5 or divided by 5 is equal to 72. So next, tessellation is also known as tiling and is created when a shape is repeated over and over again, covering a plane without any gaps or overlap. So an example of this is just like what is shown in the picture, and another example is the honeycomb, which is the storage of honey by the bees. So have you ever wondered why bees use hexagon in making honeycomb and not any other polygons? This is a type of packing problem, which involves finding the optimum method of filling up a given space, such as a cubic or spherical container. So in simple analogy, we think of a briefcase and we store clothes in it. If you properly fold your clothes, then there are more spaces to be occupied, so more clothes can be thrown inside the suitcase. While on the other hand, if you just randomly put the clothes in there, then there is a chance that it won't fit at all, so the space is not optimized. So that's the simple analogy of a packing problem from the word pack, which is to pack. So why do bees use hexagon in making honeycomb and not any other polygons? So we will prove this. Suppose you have circles of radius 1 centimeter, then each of them will have an area of pi centimeter squared. In this, we will compare the square packing and the hexagonal packing. First is the square packing. We will zoom one of the square packing. So this is it, no? The zoom version. As you can see in image 1, we connected the radius of the circle to form a square. Next, we shade the circle which is inside the square. And rotating this circle, which is colored sky blue, we will form a circle inscribed in the square. We will color it pink. So in summary, the radius of the circle is 1, while the measure of the sides of the square is 2. So the formula is area of the circle all over area of the square, or divided by area of the square. This means that this is the total or the percentage of the occupied space by the circle in the square. So the area of the circle is pi r squared, and the area of the square is just the square of the sides. So substituting the values, we get 0.7854. This means that out of the 100% of the space available, only 78.54% is utilized or is used, meaning there is at least 22% space that is wasted. So in comparison, let's look at hexagonal packing. So we did the same in the square packing, right? We connected the radius to the other radius of the circle and formed a hexagon. So moving on, we connected the vertex or the radius to the center of the circle, and we can see the hexagon is comprised of 6 equilateral triangles. So this is the triangle now with sides measuring 2. And on 4, we also shaded the circle which is inside the hexagon. So if we combine this, we can zoom this and it will look like this. So the shaded blue one is the circle inside the pink hexagon. So to find the area of the space utilized by the circle, so the area is the total area of the circles all over the area of the hexagon. So looking at the picture, we can see that the circle inside the hexagon, when we combine the 3 1/3 semicircles, so we can form another circle. Since there are 6 of it, then we can form 2 circles including the one at the center. So in total, there are 3 circles. While on the other hand, we have seen it before, there are 6 equilateral triangles inside the hexagon. So now we apply the formula, which is the total area of the circle all over the area of the hexagon, or divided by the area of the hexagon. So it equals to pi r squared times 3, because there are 3 circles all over square root of 3 all over 4 times the square of sides, which is the area of an equilateral triangle, times 6 because there are 6 triangles. Substituting the values, we get 0.9069. This means that 90.69% of the total space is utilized. So we can say that at most or at least 9% of the space is wasted. In summary, we have square packing with utilization of 78.54%, while hexagonal packing is 90.69%. So obviously, hexagonal packing is better because a few space is wasted compared to the square packing. Moving on, we will talk about population growth. It has the formula A equals P E raised to the power of RT, where A is equal to the size of population after it grows, and P is equal to the initial number of people, R is equal to the rate of growth, T equals to time, and E is equal to Euler's constant with an approximate value of 2.718. So example, the exponential growth model A equals 11e raised to the power of 0.03t describes the population of Cebu City in thousands t years after 1998. What was the population of the city in 1998? So solution, t is equal to 0 because it was still in the 1998, no? So obviously, the same year, wala pa nitubo ang population. So the population did not grow yet because it is still in the same year. Then A is equal to 11e raised to the power of 0.03t. So we substitute the values in the equation and we arrive with 11. Therefore, the population in 1998 was 11,000. So we multiply 11 by 1,000 because it is stated in the problem, no? A equals 11 times E raised to the power of 0.03t describes the populations of Cebu City in thousands. So if it is in hundreds, then we also multiply it in 100. But if it is not stated at all, then no need to multiply any number. So, okay, we proceed to another example. The exponential growth model A equals 11e raised to the power of 0.03t describes the population of Cebu City in thousands t years after 1998. What will be the population in 2060? Okay, so solution, t is equal to 2060 minus 1998. This means that 62 years have passed since 1998. So of course the population is growing because population always grows as years pass. And A is equal to 11e raised to the power of 0.03t. So substituting the values of t, we get 70.6611. Therefore, the city population will be about 70,661 in 2060. And that's all. Thank you.